Okay, good morning, all. Uh, in last lecture, we have seen the classification of inverters. I'll just repeat within a 5 minutes, and then we will proceed for the next one. So DC to AC converters are called as inverter. There are various types of inverters. As already I explained you, what is the purpose of inverter in industry, right? The purpose of inverter at home or maybe for offices is just for emergency supply, right? But in industry, the inverters are not used for emergency purpose. They are used the inverters to drive the AC drive to control the speed of AC drives, right? To control the speed of AC drives, we require a variable frequency, right? So we are having maybe a line frequency or maybe a supply voltage with a line frequency of 50 hertz, which is a constant. You may have maybe a variable voltage by using some circuits, but variable frequency, because to control the speed of AC drives, we required variable frequency, not a variable voltage. So to obtain variable frequency, we required a circuit called as inverters, right? So inverters may be drive with the help of DC batteries or maybe the AC converted to the DC. So both can be used. Every time to use the battery as an input source to the inverter is not feasible, even not economical. So conversion of supply voltage AC into DC with the help of converter, which already we learn in unit number 3, right? AC to DC converters, that is single phase or three phase, already we learn in unit number 3. So any type of converter you can use to convert AC into DC. For high power application, you use three phase converters. So three phase AC to DC converter. After some filter circuits, we get a pure DC or close to pure DC, and that DC you can use as an input to the inverter. Okay, then inverter which converts that DC into AC with fixed voltage and fixed or variable frequency, that already we have covered. So classification is also that is we have covered in the last lecture, voltage source and current source. So as per the source, DC source, DC voltage source or DC current source, according that the main classification of inverters are given. Normally current source inverters are not used, voltage source inverters are mainly used. Then classification according to the output waveform or maybe a shape of output waveform. So square wave inverter, Cauchy square wave inverter, and pulse width modulated inverter, right? So normally the output of inverter is a square wave, right? Normally in various ads we have seen that this is a pure sine wave inverter and so on, but no inverter will produce a pure sine wave. So to get pure sine wave, we can add some additional circuitry like filters and some wave shaping circuits, so that we can obtain uh, square wave to sine wave, right? Or we can get square wave to sine wave. So output of normal inverter is a square wave. This square wave is maybe acceptable at low and medium power applications, but for high power applications, we require a pure sine wave. So uh, in industry, the inverters used are a pure sine wave inverters. So they are using some filters and some wave shaping circuits so that you can convert square wave to sine wave, not a pure, but very close to the sine wave. Okay. So Cauchy square wave is also one of the type of inverter. That is a different kind of waveform. We will see that. Then pulse width modulated inverter. This is one of the most important inverter. Pulse width modulated, pulse width modulation, that already you have learned in DC or in analog circuits. So this pulse width modulation technique is used to drive the switches which are used in an inverter, and so that such type of inverter is called as a PWM inverter. Okay, then next one is a line commutated or force commutated inverter. So in AC circuits, AC line voltage is available across the device. When the current in ACR goes through a natural zero, the device is turns off. This process is known as natural commutation or natural process, and the inverter based on this principle are known as line commutated inverter. But in case of DC, because we are providing a DC voltage to the inverter, so in case of DC, since the supply voltage does not go through the 0 point, it is a constant DC. Some external source is required to commute the device. This process is known as force commutation, and the inverter based on these principles are called as a force commutated inverters. Okay, so these are the types of inverters. Then next type, series inverter and parallel inverter, and third one is a bridge inverter. So in our syllabus, bridge inverters are given. It is a single phase and three phase voltage source bridge inverter. Okay, so series inverter, parallel inverter, also the types of inverters. Uh, and bridge inverter, in which we are using half bridge or full bridge. When we use only two switches, it is called as a half bridge. When we use four switches, then it's called as a full bridge, right? So, sorry, this is the classification of an inverter. Now we will see the first circuit called as a single phase half bridge voltage source inverter. See what is the name? It may be called as a half bridge inverter. This is a single phase because definitely the voltage produced across the load, that is a single phase voltage. So it is also called as a single phase voltage source inverter. We are using here two switches, S1, S2. Diode D1, D2 are called as a freewheeling diodes. So that diodes may be used sometimes, maybe not, but with inductive load it is always used. With resistive load, not necessary to connect the diodes, but with inductive load we should connect the diode. So freewheeling diodes are connected, two switches S1 and S2, right? So this is called half a bridge because we are using only two switches, so that the circuit is called as a half a bridge voltage source. We are using here as a DC battery, ADC by 2, ADC by 2. So total is a ADC, right? So that is basically divided in a two batteries. So total voltage is equal to ADC. For example, if suppose ADC by 2 is a 12 volt and ADC by 2 is another 12 volt. So total ADC equal to 24 volt, right? So input to the inverter is 24 volt. What will be the output? That inverter produces AC. Then we use some additional transformers which will boost up your voltage and so on. That is another technique. So uh, this is a basic circuit for single phase half a bridge voltage source inverter. Dear student, again I'll repeat one thing that many times I explain you. We are showing here switch S1 and S2. Okay, so it is a symbol of a switch, but actually we are using here power BJT, power MOSFET, or SCR, or any other type of IGBT, JTO, etc. A power device, right? But we are shown here only S1 and S2 as a switch. Okay, so it's a symbols of a switches, but in actual inverter we are using the power devices. If we use power device, it means that the heatsink is always provided, that is called protection circuit is always provided from high voltage, for high current, for high temperature, right? Then gate drive circuit or base drive circuit is also provided, right? But see here in this particular figure, the gate drive circuits are not shown. The base drive circuit, that is gate drive or base drive circuits, are not shown. Even not any kind of protection circuit is also shown. But keep in mind, if we are using power devices, it means that definitely there will be a circuit required to drive or to drive the device, that is a gate drive or base drive. In case of power transistor, we require a base drive. In case of power MOSFET, in case of IGBT, in case of GTO, SCR, we require gate drive circuit. Okay. So gate drive circuit may be a UJT triggering circuit or microprocessor based triggering circuit or any other triggering circuit. Okay. So you always keep in mind that the switch, it means it's a power device, and if you are using power device, it means that that device required a protection circuit from high voltage, from high current, or maybe a high rate of change of voltage, or maybe a high rate of change of current, that is called high di by dt, high dv by dt, right? Or maybe from high temperature. So all type of protection circuits are always used with the inverter, right? If the protection is not there, definitely your device will be burned out very shortly, right? Your inverter will never work for even one day, because in a day, many times line fluctuation is there. So because of line fluctuation, temperature may be increases, so your devices may damage, right? So protection circuits are always there, but that are not shown in a figure for simplicity. Otherwise, the circuit becomes very complicated and very difficult to understand here. So for simplicity, protection circuits are not shown in a diagram, and even gate drive circuits are also not shown in a diagram. Okay, but sorry, you should keep in mind the drive circuit is always there and protection is also present in a circuit. But for explanation, for simplicity, that two type of circuits are learned separately. Already we learned gate drive circuits, already we learn various voltage protections, already we learn various current protections. So according to the requirements, you can use a different kind of protection circuits with your inverter, but that protection circuits are not shown in a figure in front of you for just simplicity. So you should always keep in mind that if we are using power device, it means that we require a gate drive or base drive circuit for the devices, power devices, and even we require voltage protection, current protection, and temperature protection. So this is very important because students many times maybe when they are in a third year, so for next semester I think there will be a mini project. So student just come with this circuit diagram and told me, sir, we want to make this voltage source inverter by using these two switches. So that is not a inverter, it is not used for any kind of load, because this circuit not included any kind of protection, right? Even not included any kind of drive circuit. So we should use drive circuit, we should add protection circuit so that you can use these circuits. Okay, so this is about the circuit. Now in this circuit we are using two switches and two diodes called as a freewheeling diode, or we can say feedback diode. These diodes are not normally used with resistive load, but the load may be either resistive or inductive, so that the diodes are always connected across the switches. So S1, S2, both are the power devices. Diode D1 and D2 are the power diodes. Okay, so it's a very simple circuit. This circuit is called single phase half bridge. Only two switches are used, so it is called half bridge, right? Input is a voltage, so it is called as a voltage source, and output is a single phase, so called as a single phase. Okay, now we will see the working of this particular circuit. Just some theoretical part is written for you. I'll just read in a short. This above figure S1, S2 are the switch. Then when the switches are closed, see the operation, that is very important, operation with resistive load. Okay, so what happens exactly? So period 1, you can see here at waveform. Okay, period 1. So when S1 is on, what happens? See, if this S1 switch is turns on, I'll just draw with the help of uh, pencil. Okay, so here S1 is on. What happens if suppose S1, S2 both are, first condition we'll see, if S1, S2 both are off. Okay, so if S1, S2 is off, so no current will flow through the S1 or no current flow through the S2. So voltage across the load is equal to 0. Voltage across the load is equal to 0 in initial condition when both the switches are off, right? When we turn on any switch, any one switch, say initially S1 switch. Now again remember, S1 switch is on, it means we are applying some triggering pulse, right? Triggering pulse should be having sufficiently amplitude and the width so that the switch may be turns on. Switch may be either BJT, MOSFET, then IGBT, SCR, GTO, any switch that is written here actually. Power BJT, power MOSFET, GTO, IGBT, any switch you can use it. Okay. If S1 is on, what happens? The current start to flow from this particular positive terminal of ADC by 2, first battery we can say, and this is the second battery we can say. Okay, so if S1 is on, your current start to flow through the load S1 and back to the battery. Okay, so this time when it switches on, so we will get a output voltage like this. This is the first part when S1 is on. Is it clearly visible to you? Because the waveform is somewhat maybe not clear actually. It is taken from the net, so it is not clear. I don't know exactly is it clearly visible to you or not. Anyone unmute yourself and just tell me, is it clearly visible? That is plus ADC by 2, right? When S1 is on, S1 conduct. S1 conduct, it means that you will get a first positive half cycle. See here, the current flows, the direction of current like this. Okay, so that time the positive here, O is positive with respect to A is negative. Okay, O and A both are the notations shown here. So okay, so someone, Ravina said the figure is clear. Thank you very much, Ravina. So A is negative and O is positive. Okay, so current flows from this positive terminal of battery to the load. It's a resistive load to the A point, then S1, then back to the P, and then EDC minus. So current O, load A, S1, point P, and back to the positive. See, the notation shown here for the battery is wrong actually. Upper is shown as a positive, lower shown as a negative. So I'll just draw as per the figure because the notations are not proper. Okay, I'll just change it for a minute. I'll just give the time for a minute. I'll just draw this is positive, this is positive. Okay, now it is okay because in a figure that they have shown positive upper and negative lower, but actually the symbol is reverse or maybe a wrong. Now I change the symbol of battery. So I again change the explanation. Okay, so if upper terminal is positive, lower terminal is negative, then current start to flow from positive, then P, then S1, then A, then back to the load. Okay, so current direction, see here, the current through the load, A is positive with respect to O. Okay, is it clearly visible? And understand what I am telling you. A is positive with respect to O. O is negative and A is positive. When S1 is on, current flows from EDC positive, P, then S1 direction. See, S1, that current through the load like this one, current flow from A to O. Okay, so when S1 is on, current flow from A to O. Okay, this is the current flow. Okay, now during second half, when S1 turns off, S1 turns off, okay, S1 is turns off and S1 turns on, S2 turns on. Now S2 turns on. Okay, when S1 turns off, again here if you are using SCR, we should remove the gate. Even we are using force commutation to turn off the SCR, because once SCR turns on, it latch into the on state and it remains in a on state. If you want to off, you should use some force commutation technique. Otherwise, SCR never turns off. For BJT MOSFET, just remove the gate bias, automatically your device turns off. That's why the BJT or MOSFETs are not a latching devices. Okay, so if S1 is a BGT, simply remove the base current, automatically your BGT turns off. If you are using MOSFET, simply remove the gate voltage, your MOSFET turns off, right? But but if you are using SCR, then we should use some force commutation so that the holding current should be less than, or maybe your forward current or current through the SCR should be less than holding current so that your SCR turns off. Otherwise, your SCR never turns off. Okay, so keep in mind, if you are using SCR, then you require a force commutation because the input is a DC. If input is DC, it means that you require a force commutation to turn off the SCR. Okay, so in this particular circuit, we are considering simply a BJT. So just simply remove base current, automatically your BJT turns off. So S1, the base current of S1 remove, S1 turns off. At the same time, base current to the S2 should be applied. Both are transistors. Huh? I'll write it T2 and T1. Okay, so that you can easily understand. Transistors, even simply BJT. Okay, you can understand T1 and T2. So this T1, transistor T1, BJT, base current remove, immediately your transistor turns off. Okay, at the same time, base current to the S2 should be applied. Okay, so what happens now? The current from this lower battery, positive, then to the load, then S2 and back to the negative battery. This time the direction of current is reverse. You can see here the current is reverse. It means that O is positive this time with respect to A. A is negative, right? A is negative, O is positive. So that you will get a negative half cycle. See this one. S2 on, S1 on. S1 on, that time you will get a positive half cycle. Definitely it's a square wave. And when S2 on, you will get a negative half cycle, right? This is called as a current of SCR. This is a load current and this is voltage across SCR. If SCR or BGT, if SCR or BGT is on, the voltage across that device is very small. That is ideally zero, and practically the voltage across the device when device is on is equal to 1 volt. Okay, even SCR 1 volt, BJT just zero point 0.7 volt, MOSFET, it voltage across MOSFET when it is on is equal to threshold voltage. So it may be a more than 3.5 volt. Okay, so it depends upon the power devices. Different power devices having a different voltage drop. So according to the use of power device, the voltage drop will be shown here. When the particular device S2 is off, that time the complete battery voltage is applied across the switch and so on. So current waveform and load voltage waveform, the shape of both waveform is same. Keep in mind, these are the current for S1, this is current for S2. It means triggering pulse for S1, triggering pulse for S2. This next waveform is a load current. When S1 is on, that time you will get a positive current. When S2 is on, you will get a negative current. Again S1 on, positive current and so on. And this is voltage across the device. If device is off, the voltage across device is equal to just 1 volt. And when device is off, that time voltage is equal to the EDC. Voltage equal to EDC, not EDC by 2, because the voltage, this voltage and this, both voltage will appear across that particular device. So that when device is off, that time the voltage is equal to EDC. Keep in mind again this one, right? So whichever switch is on, the voltage across that switch is equal to voltage drop, that is maybe equal to 1 volt or maybe 3.5, maybe 0.7. It depends upon a power device. Okay, so this is the output waveform. Now see, operation is shown here and even working is also given for your study purpose. Okay, this working is sufficient. These waveforms, when you draw, if you draw this particular diagram, proper notations and explain how to explain. So initial condition first, when both the switches are off, if S1 S2 both are off, no current flow through the load. That time output voltage equal to 0, output current equal to 0, This is the first case. Case second, when S1 is on, S1 is on, it means by applying triggering pulse, S1 is on. If S1 is on, current start to flow from EDC plus P, then S1, then A, then load O and EDC minus. Okay, see here, the same kind of explanation is given here. So I just read the explanation once because this type of explanation I have added every time for every circuit. The explanation is added. Whatever theory that I explain here, the same theory is added here for your reference use. It means for your notes purpose and so other. So see what I told you, the same is written here. Switch S1 is closed for half time period, that is T2 by 2 of the desired AC output. It connects point P of a DC source to point A, and the output voltage E0 becomes equal to EDC by 2. At T equal to T by 2, getting signal removed from S1 and it turns off, right? Getting signal removed if it is used BJT, MOSFET, other devices. But if you are using SCR, simply getting signal removed is not sufficient to turn off the device. We should use some additional circuitry called as a force commutation circuitry to turn off the device. Okay, for the next half time period, T2 by 2 is T is greater than T2 by 2 and less than by T. The gating signal is given to the S2. It connects to the point N of the DC source to point A, and the output voltage reverse. Thus, by closing S1 and S2 alternately for half time period, a square wave AC voltage is obtained at the output with resistive load. Wave shape of load current is identical to that of output voltage, right? Simply by controlling the time period of a gate drive circuit, the frequency can be varied. This is most important. Today or tomorrow, I'll just post practical number 6 and 7 on YouTube. I'll share the link of the same. You can observe the practical number 6, that is PWM inverter, in which I have shown how the frequency is varied, right? So simply see here, frequency of this particular waveform is equal to 1 by T, right? Total T is equal to this one. See, this is a T, okay? So just 1 by T is your frequency, right? So if we change the on time of S1 and S2, we can simply change the T. If T is changed, it means frequency is changed. It is very simple to understand, right? How to change frequency? By simply changing on time, off time. So it is in our hand how much time S1 is on and how much time S2 is on. If suppose S1 is on for 5 milliseconds, right? And S2 is on for 5 milliseconds. So what will be the frequency? Total time equal to 10 millisecond. So frequency equal to 1 by 10 millisecond. It will be 100 hertz, right? So we can easily change the on time of a T1 and T2 by providing the gate signal, by removing the gate signal, by providing the base signal, or by removing the base signal, right? So the gating circuit is most important here, right? Because according to the required frequency, we turn on and turn off these switches alternately, we get the variable frequency, right? If I on S1 for 0.5 millisecond, right, and S2 for 0.5 millisecond, so total T equal to 1 millisecond, the frequency of inverter is 1 kilohertz, right? 1 divided by 1 millisecond equal to 1 kilohertz. So we can have a variable frequency, right? Simply by changing on time of S1 and S2, right? See, one most important thing should be remember, the on time of S1, S2 should be same, right? So that you will get a proper square wave. Otherwise, you will get something different kind of waveforms. So to obtain a proper square wave, the on time of S1 should be exactly equal to the on time of S2. So if S1 is on for 0.5, then S2 must be turned on for 0.5 so that you will get a proper square wave, right? Total time equal to 1 millisecond, 1 divided by 1 millisecond equal to 1 kilohertz. So you can easily change the frequency of inverter by changing the on time of these two switches, right? And that is given here. Simply by controlling the time periods of a gate drive signal, the frequency can be varied. Here diode D1, D2 do not play any role. Basically, these D1, D2s are required with the inductive load. So, but I already told you that the same circuit is used for inductive, just load is replaced with resistive with inductive. So you can use the same circuit. So the diodes are work as a freewheeling diode with inductive load. We will see the operation with inductive load even, but the gating circuit should be designed such that the switch S1 and S2 should not turn on at the same time. This is another important thing. The gating circuit should be designed. If S1, S2 both should be turned on, then definitely this circuit will never work as an inverter, right? So the gate drive circuit should be designed properly so that the on time of S1 is exactly same as the on time of X2. At the same time, the S1 and S2 should be turns on at the should not be turns on at the same time. So these are the two important things that we should keep in mind. Okay, then okay, whatever the circuit working I explain you, if you are having any doubt in this particular explanation, you can ask me. Otherwise, we'll go for the circuit analysis. Yes, I'll just give you 1 minute uh, for your attendance. So everyone start to give your attendance in a chat box. One more thing, after giving attendance, if you leave the class, then I will mark your attendance as absent. Okay, so start to give the attendance in a chat box privately, and during this particular 1 minute you can ask me the questions. Okay, Kanchan, you have raised your hand. Whatever your question, to please. Okay, you're having any question, you can ask the question in a chat box. You can unmute yourself and ask me. Okay, because I'm not maybe mute the students. You can unmute by yourself and you can ask me any question. If suppose not possible to unmute yourself, you can directly write the question in a chat box so that I can read the question in a chat box. If any question, you are having any question regarding this one, you can ask me. Some students have raised their hands, but I don't know exactly how to see your questions. Where is the chat box? Okay. Okay, any question? If I'm having any question, you can ask me. Okay, so anyone? Okay, okay, Kanchan. Okay, by mistake. Any other? Okay, no question. So can I understand? Maybe start the next part. Okay, no response. It is very, very unfortunate and painful for the teacher. Actually, if you are not uh, ask any question, I don't know you are having any question or not, but at least you can write here no question in a chat box so that uh, we can proceed for the next one. Otherwise, uh, difficult to understand the problems of a student. One student has left the meeting, so I'll just take a snapshot. And those who left the meeting after giving attendance, I'll just put their attendance as upset because are having maybe a mobile phone. So I just join the meeting and immediately I'll take a snapshot. One student already left the meeting. So this is a very bad thing after giving attendance if you left the meeting. So this is not a good. Anyone can mute yourself. Okay. Now I'll just take a snapshot of. Just 1 minute. Okay. So the last 1 minute is remaining, but from your side, no question. So we'll go for the circuit analysis. I know that this topic will never cover in a today's lecture, but at least we'll start. See here, the output of this circuit is AC, right? So we have to find out the RMS voltage, RMS output voltage. But to find RMS output voltage, first we should know that the average value of output voltage, right? An average value of output voltage is calculated by using integration. So EO average equal to 1 by 2 pi integration 0 to 2 pi E0, that is output voltage, omega t d omega t, right? So RMS value of output voltage, right? It is under root of the above value. So you will get just the EDC by 2. When you solve this particular integration, you will get EDC by 2 as an output. Keep in mind, this is very